All right. So, if you would please, let's get out our notes. We have so much time and so little to do. Wait.
I think it's the other way around.
Strike that, reverse it. Okay. So, today what we're looking at are two methods for approximating function values. Okay. Two methods of approximating function values using calculus. All right. The first one is something we've kind of already done before, using a tangent line to approximate the value of a function. Okay, because we know that a tangent line near the point of tangency. Okay, so the tangent line near the point of tangency is a good approximation to an actual function, right? So here, for example, in this picture, you can see a curve, right? So this is like f of x right here, we'll say. Okay, whereas this is the tangent line to f of x at, and I don't know, we'll say at this point like right here. Okay, at AB. Okay, so there's that point AB, that point of tangency. Okay, right there. And you can see, of course, you can see, all right, how close this tangent line is to the actual curve, right? In fact, at some point, you kind of can't distinguish between the two. They're so close to one another. And so near that point of tangency, the tangent line is a good approximation, okay? Also known as the local, because nearby, right, linear for the line approximation. So tangent line approximation, local linear approximation, mean the same thing. Okay, and so for these first two examples, we're going to be looking at just writing the equation of a tangent line and then using that tangent line to approximate the particular value of a function. Okay, so number 5, approximate the value of f of 3 using the tangent line to f of x equals that at x equals pi. Okay, so we're going to use pi, x value of pi, to approximate the function value at 3. Okay, if you look here, right, at trying to plug in 3, like right now off the bat, right, if we were trying to evaluate 3 here, it would be kind of challenging to do that because we don't know how to find like the sine of 3, right? Okay, so like f of 3 equal to the square root of 4 plus 5 sine of 3. Okay, how are we going to evaluate that, right? What is the sine of 3? We don't know that off the top of our heads. All right, now, we could, I guess, actually, just plug x equals pi in for this right here and then approximate, 3 using just f of pi there. But we're going to use a tangent line to approximate, okay, instead. So, what do we need in order to write the equation of a tangent line? We need a slope and we need a point, okay, or point and slope, whichever order you want to give those in is fine, okay. Let's do the point part first because that's maybe easier to do, okay. Do we know any information about our particular point that we want to use? X is pi, right? Again, we want to approximate f of 3, so you might think, oh, we should use 3. No, we want to use pi. We're using the tangent line to this at x equals pi. So our x coordinate's pi. How can we find its matching y coordinate? What do? Plug it into the equation f. Okay, so we want to find f of pi, which is equal to the square root of 4 plus 5 sine of pi. Okay, sine of pi, 0 times 5 is 0, plus 4 is 4, square root of 4 is 2. And so we get the point pi 2. Okay, and then how do we find the slope for our line? Take the derivative, right, because we're trying to find a tangent line. Tangent line's slope is based off of the derivative of our function there. So the slope part, okay, we'll do f prime of x. Oh boy, we're taking the derivative. We haven't done that in a while, right? So remember, that's 4 plus 5 sine x to the 1/2 power. So we're going to bring that 1/2 out front. Leave what's inside there to the negative 1/2. Okay, times the derivative of what's inside. Derivative of 4 is 0. The derivative of 5 sine. Derivative of sine is cosine, so it's going to be 5 cosine of x. Okay. I'll rewrite this here just a little bit. So let's see here. Since it's 4 plus 5 sine x to the negative 1/2, that's going to go in the denominator. The 5 cosine is going to go in the numerator. So we'll have 5 cosine x over 2 times 4 plus 5 sine x to the positive 1/2 power now, since I moved it to the denominator. Okay, that's just a little manipulation there, just for our, just for simplification's sake. Okay, and then we'll do f prime of pi. Okay, we're going to plug that pi in, because again, that's where our point of tangency is going to be. So we'll just plug pi in here. So it'll be 5 cosine of pi over 2 times 4 plus 5 sine of pi to the 1/2. Okay. And we'll evaluate that. Cosine of pi is -1, so we get -5 in the numerator. Let's see, your sine of pi is 0 times 5 is still 0, plus 4 is 4, square root of 4 is 2, 2 times 2 is 4. So we get -5/4 there for our slope. So the equation of our tangent line then, y minus 2 equals the slope m, -5/4 times x minus pi. Or solving for y, we get y equals, -5/4 x minus pi plus 2 there. So again, you could stop here if you're just trying to find the equation of the tangent line, but remember, we're not trying to find the equation of the tangent line. I mean, that's part of it, but our ultimate goal is to use the tangent line to approximate f of 3 at pi. So now that we have the equation of the tangent line, what do we do now to figure out the value at x equals pi? Plug in pi. Exactly right. Now we're going to plug in pi, and so we get y is 2. Okay. Maybe I should write this a little bit better. Y evaluated at x equals pi is 2.
Wait, aren't you supposed to do 3?
Approximating it to 3. Exactly right. Sorry, my mistake. Yes, we're approximating f of 3 at the tangent line at pi. Yes, sorry. It should be f of, we should evaluate y at 3. Thank you. Goodness gracious. All right. So we plug the 3 in, so it's -5/4 times 3 minus pi plus 2. There we go. Okay. So the 3 goes in for x. Yes, Sean?
So just make sure I understand this correctly. So if we take the point that we had, we said the pi, and we plug it into the derivative, that's going to give us the slope at that point.
Slope at that point, exactly right. Just like we've always done. So,
That's all I'm confused about.
okay, cool. And so then that as a decimal is approximately 2.177, we'll say. Okay, approximately as a decimal, 2.177. Okay. Of course, if we had our calculators in this case, we could find the exact value of f of 3 used by just plugging in 3 in the first place, right? So, but anyway, there's the approximate, and of course, there's the exact value right there. Okay. And in fact, if we do type this into our calculator, let me just make sure here I'm in radian mode. Okay, if we actually type in f of 3 here, the square root of 4 plus 5 sine of 3, we get about 2.169, which is close to that 2.177, pretty close. Okay, off by 1/100. Okay, so that's the idea there. Alrighty. Questions on that process? Okay, so let's try the next one here, number 6. Approximate the value of f of 1.02 using the tangent line to now f of x equals this function at x equals 1. So we want to find the tangent line of this function at x equals 1, and then also determine, is this approximation an over approximation or an under approximation? Okay, over or under estimate. Okay, and then we'll explain our reasoning. All right, so again, same process as before. We'll find our point and our slope. Okay, the point of our tangent line is going to be, well, again, we have the x-coordinate. What do we do with this x-coordinate to find the matching y-coordinate? Plug it into f. So we have 1 comma f of 1, which f of 1 is 5 minus 3e to the 2 times 1 minus 2. Okay, 2 minus 2 is 0, e to the 0 is 1, times 3 is 3, so we get 2. So 1, 2 is our point. Okay, the slope, how do we find the slope of a tangent line? Take the derivative, and so we get f prime of x here is what we're looking to find. The derivative of 5 is 0. The derivative of negative 3 e to the 2x minus 2, well, it's going to be negative 3 e to the 2x minus 2 again times 2, the derivative of what's inside. What's inside is the inside of the exponent. The derivative of 2x minus 2 is just 2. So it's negative 6 e to the 2x minus 2. And then we want to evaluate the slope at 1. Again, we want to find the tangent line at 1. So f prime of 1 equals negative 6e to the 2 times 1 minus 2. E to the 0, right, is what that's going to be. So we get negative 6 for our slope. So our tangent line is y minus 2 equals negative 6 times x minus 1. Or y equals negative 6 times x minus 1 plus 2. Okay. And then we want to evaluate this at 1.02, right? Because we want to approximate that value of 1.02. So y evaluated at x equals 1.02 will be negative 6 times 1.02 minus 1 plus 2. Okay, 1.02 minus 1, 0.02. 0.02 times negative 6, it'll be negative 0.12 plus 2. And so we get then 1.88 as our approximated value there. Okay. Question?
When it says explain your reasoning, are they looking for words or just words?
Well, so the explain your reasoning is for the is this approximation over or underestimate?
Oh, okay.
That part. Okay. So we're talking about using tangent lines to approximate our curve, right? There are particular properties of our function, okay, that determine when a tangent line is above our curve and when a tangent line is below our curve. Okay. Does anyone recall what behavior determines whether a tangent line is above or below the curve? It is concavity, exactly right. Okay. In fact, when we first talked about concavity, we talked about not only concave up looking like a cup and concave down looking like a frown, bless you, we also talked about how concave up the tangent line was, well, let me draw an example here. Here's concave up. Imagine drawing tangent lines here. Tangent line, okay? The tangent lines are below, okay? They underestimate our curve, whereas concave down, our tangent lines there overestimate, right? There, the tangent lines are above our curve, okay? So, concavity determines whether the approximation or whether the linear approximation or the tangent line approximation, I'm going to do that, whether the tangent line approximation is an overestimate or underestimate. Okay? A linear approximation or tangent line approximation is an overestimate when we are concave down, and an underestimate when we are concave up. Okay? When in doubt, draw a picture to help you remember. Okay? You don't necessarily need to draw a picture of the actual function itself. Just draw a picture of concave down behavior or concave up behavior. Draw your tangent lines in there to convince yourself, oh, right, concave down, the tangent line is over an estimate. Concave up, the tangent line is under my curve, so it's an underestimate. Okay? For our purposes here, then, we have to determine the concavity of this function. How do we determine the concavity of a function? Look at the second derivative. Now, we already have the first derivative right here, so we're just going to take the derivative one more time. Okay? So the derivative of negative 6e to the 2x minus 2 is negative 6e to the 2x minus 2 times 2, so it's negative 12e to the 2x minus 2. And we're not interested, we're just interested in whether that is going to be what? Positive or negative. What do we know about this? Always negative, right? Because we got e, which is a positive number, okay? 2.6 something, right? To a power. So a 2.6 to a positive or negative power will still be a positive value, times then a negative number will be negative, okay? So, f is always concave down for all x, since f prime prime of x is less than 0 for all x. Thus, f of, well, let's say this. Thus, 1.88 is an underestimate, or sorry, overestimate, concave down, overestimate, okay, for f of 1.02, or an over approximation for f of 1.02. Okay, something to that effect is our final answer there. So there, Simeon, is the reasoning that we're looking to come up with. Okay, that kind of reasoning, that explanation. Okay. All right, and if we actually found f of 1.022, you can, type that into your calculator and stuff like that, and we actually get f of 1.02 to be about 1.877. So 1.87, our linear approximation here, is an overestimate. 1.88 is higher than 1.87, right? So if you actually found the actual value there using calculator, you can see it would in fact be an overestimate. That's true. Okay, questions on that method there? So that's nothing too terribly new, okay, just kind of an application of stuff we've already been doing, but just kind of rehashing it, maybe a little bit more explanation, of course, with the over or underestimate. Okay, just using the tangent line to approximate the curve at points near that curve. Okay, the next method we have is Euler's method, okay? It's a numeric approach to approximating a particular solution to a differential equation, okay? In this particular case, it's helpful for situations where you can't necessarily find the original function, okay? So finding particular solutions to a differential equation that may be too difficult to separate given a starting point to the original function. So you need to have a starting point, right, an initial condition, okay? And then you can find, additional solutions to that differential equation, okay? You don't come up with a function, you just come up with what, like, another value of that function will be, okay? Kind of thing. So it finds a value, but not the actual function itself. Okay. The main idea here is you have like your starting point. Okay. So we'll have the starting point like x sub 0, y sub 0, right? That starts, stands for initial x, initial y. That point. Okay. You need to start with a point that's on the curve. Okay. It doesn't really matter where you start. All right. And then you want to have like a final goal in mind too, okay? So for example, if you look at example 7 here, we're trying to approximate the value of the function at 0.2, and we're starting at an x value of 0, okay? And so you want to have a starting point and then an end goal in mind. And the idea then is to use your starting point and your differential equation. You plug your starting point into the differential equation, get the slope of your tangent line at that point, and then use the slope of the tangent line, which is going to be a number, right? A rise over a run. You're going to rise that much and run that much to another point, then find the slope of the tangent line at that point. You get a new slope, and then again use the rise and the run from that slope to get to your next point, so on and so forth. Continue to doing those steps until you get to your desired x coordinate location. You can see here that it is not going to be perfect, right? You can see the error starting to grow. In fact, as we move away from that starting point, it's not a bad approximation. Then we get to this point, and then we readjust, right? A new slope, rise and run up to this point, It's still, you can see the error growing though between what it's supposed to be and what it is, right? The approximation versus the real, okay? And as you go, the more error you're going to kind of accumulate there potentially, okay? So, and of course we'll use a similar concept for the over and under estimate as well. All right. So, again, we're looking to approximate the value of the function at the x-coordinate 0.2. We're given that at 0, x-coordinate 0, the y value, the function value is 2. And we're going to again use this linear, or not this linear, this differential equation. And we're going to use 2 steps. Okay? So in other words, we're going to do 2 applications, so 1, 2, of the Euler approximation here, or the step here for the Euler approximation. Okay? So again, our goal is to start at x equals 0. We want to end at x equals 0.2 in 2 steps. Okay, 2 equal steps. Okay, 2 equal steps. So what will the size of our steps have to be? 0.1, right? To get from 0 to 0.2, we need to step 0.1 at a time. Okay, and so to do this, I'm going to have you guys set up a table here to kind of just help organize our work. Okay, so we'll start with our x and y coordinates. Okay, we're then going to add in our dx here, our change in x, our step. Okay, this is also like, you can think of this as like the step. Okay, a small step or change in x. Okay, then we'll find the resulting change in our y using this differential equation, but with the dx multiplied over to the other side. So you can see it's dy equals y plus x dx. So we have our little change in x. We already know what that's going to be. You guys already said it's 0.1. Right? That's our step. We're going to move 0.1 each time. We're going to do 2 rows of this. Okay? And then we'll take the resulting change in x and we'll add that to our original x coordinate here. And then we'll take our original y and add the change in y based off of the differential equation there. And that's going to give us our new point. Okay? So, our starting point goes right in here. Where are we starting again? 0, 2, right? 0, 2. Okay? And so we already know what our new x-coordinate is going to be. It's going to be 0 plus the step of 0.1, right? We're going to take one step towards that x-coordinate of 0.2. So we take one step towards it by adding a 0.1 there to the x. And now we have to figure out what our y is going to be. We already know where we're starting. Our y is starting at 2. We're going to have to add to it some change in y. What change in y? Well, we're going to use our differential equation to figure out that little change in y that we need here. Okay? So dy is y, which is 2, plus the x, which is 0, times dx, which is 0.1. Okay? So 2 plus 0 is 2, times 0.1 is 0.2. And so we're going to change our y value is going to change then by 0.2 according to our differential equation here. So in other words, this point is the point now 0.1 comma 2.2. Okay? So that's after one step. But again, we're taking 2 steps here. So we're now going to take this new point that we produced and apply one more step to it. Okay? So we're going to go from that 0.1, 2.2, apply Euler's method here to the step again. Our step for dx is still going to be 0.1. And so again, we already know our x-coordinate here. It's going to be 0.1 plus 0.1. Oops, I should not have closed the parenthesis there. Comma. Okay, we already know our y. Our y is 2.2. We just got to figure out what we're going to add to that y. Again, using our differential equation. dy equals 2.2 plus 0.1 times our dx of 0.1. Okay, so 2.2 plus 0.1, 2.3. 2.3 times 0.1, 0.23. Okay, So 2.2 plus 0.23. This will result in an x coordinate of 0.2. Aha! We have gotten to the x value that we're trying to, approximate, the y value, 2.43. Okay? And so using that approximation, we can say now y of 0.2 is approximately 2.43. Okay? And that will be our approximation. Okay? That's our approximation. Can we find the actual value of y at 0.2? What would that involve here with our differential equation? We would need to do what? Separate variables and try and solve it. But if we separate our variables here, we end up with dy equals y plus x times the quantity dx. And so we're like separate variables here, right? Maybe. But you can see that I'd have to subtract y over to get it with the dy, but then it would be like dy minus y instead of y dy, y times dy. So no, this won't work, okay? We can't separate y's and x's, so we can't find y of 0.2 exactly. Okay, so just can't do it. All right. Can't do it. But we can determine if this is if our approximation here is an over or under approximation, okay? And it's going to be the same principle as we did before. We want to check the concavity, okay? So again, in order to talk about concavity, we need to be looking at the what? Second derivative. We have the first derivative, so that means we have to take the derivative of this thing with respect to x. So the derivative of dy dx with respect to x is d squared y over dx squared equals, what's the derivative of y with respect to x? dy dx. What's the derivative of x with respect to x? 1. Okay. And then we know what dy dx is, don't we? It's y plus x. So we can rewrite this as just y plus x plus 1. Oof, we have y and x we have to worry about here. Can we safely say that this is going to be always positive or always negative? No, but for our interval, can we say it will always be positive or always be negative? Yes, we can, right? Because our x values go from 0 to 0.2. Our y values go from 2 to 2.2 or even 2.43 if you want to say there for our final step. Okay, they're both positive. You're going to add them together plus a 1. That will be greater than 0. Okay, so from x equals 0 to x equals 0.2. Okay. D squared y over dx squared is greater than 0. So y is concave up. Right, since our second derivative is greater than 0, y is concave up. And so then we would expect our approximation to under or overestimate. Underestimate, okay? Okay. So y of 0.2 equal to about 2.43 is an underestimate. I'm running out of space here. Of y of 0.2. Okay? Sorry about that. I know it's like way squeezed down there. I'll zoom in some more. Okay. So establishing that our second derivative is positive for that interval, y is then concave up on that interval, so y of 0.2, which is approximately 2.43, is an underestimate of y of 0.2. Okay? All right. Moving on. Questions on any of that so far? All right. So we'll do this 2 more times here. similar kind of situations. All right. We're going to use Euler's method again. For y equal to f of t, we're going to start at the point 0, 9. We're going to use two steps, again, of equal size to approximate now f of 1. So we're trying to move from f of 0, which we know has a y value of 9, to f of 1. So what will our step size be in this case? 0.5, right? We're going to go 0.5. So now instead of x and y, we'll do t and y. Okay, dt, okay, is always going to be 0.5 for both of our steps. Okay, again, we're going from t equals 0 to t equals 1 in 2 steps. So dt equals 0.5. So I'm off the screen. There we go. Okay. Our differential equation, well, remember, f prime of t, we can rewrite that as just dy over dt equals y over 3 times 6 minus y, right? I mean, f prime of t is dy dt. Okay, we can say that too. And so then our differential equation we'll say is dy equals y over 3 times 6 minus y dt. Put a little dt there at the end, right? Multiply it over. Okay, and then we'll take our old t and add our little step to get us closer to that point that we're trying to approximate. And then we'll take our y and add its little step based on the differential equation there, okay, to get us to, again, that point we're trying to approximate there. Okay, our starting t and y, 0, 9. We already know what the new t is going to be after this step, after our first step here. It's going to be 0.5, right? So I'm just going to go ahead and put that there. Because we're just doing 0 plus 0.5. Okay, and now we'll do the dy. So dy here is 9 over 3 times 6 minus 9. And then dt is 0.5. Okay. 9 over 3, 3. 6 minus 9, negative 3. Negative 3 times a positive 3, negative 9, times 0.5, negative 4.5. Okay, so we're going from a y value of 9, we're going to add to it a change of negative 4.5, and so we result in 0.5, comma 4.5. 0.5, comma 4. Question, Sean?
So, when we're doing this method, we take the original, like the t or the x, y, and then dt, how do we find that? Where is that?
dt is based off of kind of taking our total interval. So we're trying to go from a t value of 0 to a t value of 1, and then dividing that total interval by the number of steps. 2 steps in this case, right? 2 steps of equal size. So 0 to 1, that's a total distance of 1, dividing it by 2, 0.5. Okay? And we use the derivative then, because so this is going to be like our steps for the x no matter what, and then we're going to use the derivative to come up with then, well, if that's our step for our x, what is our step for our y? What's our change in our y going to be? What's our resulting change in our y going to be? Yep.
So since it was, you're trying to approximate f of 1, we divided that by 2.
Because we're trying to approximate f of 1, we found the distance from our starting point, 0, to 1, length of 1, divide that by 2. So it's not the ending point that you divide by 2, it's the distance between the starting point and the ending point, the x values. Divide that by the number of steps. Okay, that tells you how many steps you have to take, right? So 2 steps. Okay. So we have our new starting point here, 0.5 and 4.5. Okay, plug this into our dy. So now it's going to be 4.5 over 3 times 6 minus 4.5, and then dt is still 0.5. Okay. 4.5 divided by 3 is 1.5. 6 minus 4.5 is also 1.5. And then times 0.5. Okay. And this ends up being 1.125. 1.5 times 1.5, 2.5. There we go. Okay, 2.25, sorry, 2.25, and then times 0.5 gives you the 1.125. Okay, and so then we'll put this in here. So we're going to take our dt, which is 0.5, we're going to add another 0.5 step to it. Then we're going to take our y, which is at 4.5, and add the new step of 1.125 to it. And so we result in 1. Aha, we're at that t value that we wanted to get to, 1. And then we'll add these two together. We get 5.625. Okay, 5.625. So we'll say that f of 1 is approximately 5.625. Okay. Now it's saying, then solve the differential equation to find f of 1. So this is not even can you solve it, this is solve it. So we can solve this. Does anyone recognize this differential equation format? It's logistic. That is right.
Say what?
Say what? Okay. What indeed? So, oops. Let me not step over bounds here, right? So, well, what should we do here to kind of get this in the typical logistic format? Factor out a 6, right? Remember, we want it to be 1 minus, okay, y over L here. And so we need to factor out a 6. And so if we factor a 6 out, 6 in front here, 6 times the y over 3 will be 2y. So dy over dt is now 2y times 1 minus y over 6. Okay, right? We just factored out. Okay, in this case, factor out the 6. Right? All right, we know then that that's our differential equation. We also know how to come up with the original function, right? Y equals L over 1 plus B E to the negative k. What's our k value based off of our differential equation here? 2, so negative 2t. Okay. How can we find the missing b value? What do we know as a point that's on our curve? 0, 9. So now let's plug in. We use 0, 9 to find b. So we have 9 equals 6 over 1 plus b e to the negative 2 times 0. Okay. Negative 2 times 0 is 0. E to the 0 is 1. So we have 1 plus b. 6 over 1 plus b. Okay. Which, if you'll permit me here, I'll multiply both sides by 1 plus b and then divide both sides by 9. And I'm going to end up with this. That might be a lot of, I skipped kind of 2 steps there just to kind of save space. Okay, 6/9 is 2/3, but subtract 1 from both sides, so b will be negative 1/3. Okay, b's going to be negative 1/3 there. Okay. And so since b is negative 1/3, now we have y equals 6 over 1 minus 1/3 e to the negative 2t. And of course, we want to use this to find the exact value of y when t is what? 1, right? That's what we were trying to find in the first place. So we'll evaluate y at t equals 1. 6 over 1 minus 1/3 e to the negative 2 times 1. That's the exact value. Okay, which is approximately, when you type it in your calculator, approximately 6.283. Okay, which you can see, it's not that close. I mean, I don't know. It depends, I guess, on how close we need to be, right? But I mean, they're not that far off, but they are that far off. I don't know. So I mean, there's our approximation. There's the exact. Okay, it really depends on, you know, our preferences as far as like how far off we're okay with being. All right. Questions on any of that? Okay. So So let's try number 9 here then. Approximate the value of f of 1.7 given f of 2 is 5. Now, this is a little bit weird. In the first Euler method that we did, the point we were given was 0, 2, and we wanted to get to 0.2, right? So we were given the x value of 0. We wanted to find the y value at 0.2. We went to the right, right? We moved from left to right. Here also, we were given the f of 0 is 9, and we wanted to then get to f of 1. So we had to move from 0 to 1. But now here, we're given the value of the function at 2 and asked to go back to 1.7. Okay, so that's a total of how far distance? Negative 0.3, and we want to do that in 3 steps. So negative 0.1 will be each step here. Okay, so again, it's going to be, it's like 1.7, 1.7 minus 2 over 3 steps equals that negative 0.1 step size. Okay, or it equals dx, you can say it that way. Okay. So, why don't you guys try this one out here? Okay, our starting point again is 2, 5. Our dx, our change in our x, negative 0.1 for all 3 steps. And then our dy, our change in y, is the quantity 2y plus x times dx. And then we've got x plus dx there, y plus dy. Okay. You can see here, this kind of like method is like ripe for a programmer to, to work out. This is a great idea because, of course, we're doing these like very repetitive calculations and stuff like that that a computer is just a deal for, right? So.
Sure.
Right there, Lily, 1 second. Actually, I'll just go right now. General question.
For this one, would we be allowed to have a calculator?
Good question. So,
Dude, what is
so
12
at
times
no
12?
point, right, so I guess it wouldn't necessarily be required, no. It would not necessarily be calculated after.
Oh well.
You're gonna make us multiply decimals?
Yeah.
I haven't done that.
It's just moving the decimal place over.
Sometimes,
On 0.1.
Yeah.
But then it's negative. So
I will say this, Lily and like Mario, generally they try to give you, they don't try to make it like too
Like, these
messy.
are really, these are a little beyond my brain.
They're testing you?
ability.
Okay, well,
I could do the other thing.
I mean, I'll try, okay, let's try this step right here. Okay, so dy.
One, okay,
Yeah, the first one's
First one's easy enough. Okay, I gotcha.
Yeah.
I don't know, the second step is going to be 7.6 plus 1.9
Yeah,
Times 3.8.
times negative 0.1, which also isn't that bad because, again, it's just moving the decimal place, right? When you multiply something by 1/10, you just move the decimal place.
No.
Because it's multiplied by 1, but then it's 0.1, so you just move the decimal place.
Not having it.
yeah.
Yeah.
Wait.
Here's the answer.
Then you have to subtract it, and then you have to
Yeah.
do again with
Oh, wait, no,
that's
no.
your number.
True.
I mean, I can do it. It's just going to take a lot of separate multiplication of decimals.
I see what you're saying,
I'll just
yes.
say-
Well,
Take a lot of time.
I gotcha.
Say no to it.
Can you do this all your guys?
Watch. Oh, no, he doesn't have to use this calculator. He already did it.
He already has the answers.
Did you use a calculator to find the answer?
Me?
Yeah.
Yes.
Probably.
To speed myself up, yes.
Glad we're all on the same page.
Okay, so there, I'll give you your first step. Because obviously, if you make a step in your first step, you're just going to trickle down, okay?
What points are these normally worth? Like,
That is a good question. I don't
if you make a
know.
mistake, could you still get future points?
I would imagine so, yes. I imagine you but that's a good question, sir. I don't know. I'll have to check on that because
I don't know how to
Yes.
multiply a fraction. I don't know how to subtract. That's even harder.
Alright, we only have 2 more minutes.
That's so sad. I don't want to go to my next class. It's so sad.
I don't wanna go to
You're taking a dumb test that doesn't even matter. It doesn't even affect your grade.
You're not good at second one.
I'm dropping the class. I don't even have to take it.
But you still have to take the final.
Yeah, I can get a 0 in the final. I still have an A.
Really?
Yes.
Are you sure?
Yeah.
It doesn't sound right.
Is it weighted the same as everything else?
It should be. Why would she wait?
Okay.
Why would she wait somewhere else?
The final?
Shut up.
If you
Why
want
would
to use
you
a
not
calculator to
find
help
this
you
also?
speed things up for this, I mean, feel free, okay? If you want to use a calculator to help you speed things up. Okay.
So I'm pretty sure this final is 20%.
Because it is a little tedious enough as it is with all the calculations to then also have to add on the arithmetic to it. But I will say, this could be non-calculated.
I'm pretty sure if you don't do anything and you just turn it in, I'm pretty sure she'll give you a 0 no matter what.
No, you can just bubble in whatever answers you want. You get a 0.
If you're done and you're feeling good, the homework is the next page in the notes, the front and the back.
Is it the front and the back?
Front and the back. Well, yes. Yes. Front and the back. Okay? So again, if you're done, you're feeling good, if you want to start looking at the next page of the notes, the Euler method worksheet, that is your homework for tonight. Okay? I'll give you those you still work another like minute or two here to finish up these calculations.
Are we allowed to use a calculator for homework?
Say again?
Are we allowed to use a calculator?
Are you allowed to use a calculator on... it doesn't say whether you can or can't. I think you should try to not use one.
So you want us to use the Euler's method, right?
If it says to use Euler's method, use Euler's method.
But for number 3, are we allowed to just plug it in?
Number 3, you're supposed to use the tangent line to approximate, not Euler's method.
It's called reading the directions.
So write the equation on the tangent line. Yes?
Was that express permission to write a code so that I don't have to do the homework?
I mean, you can if you want to, sure. But you're going to do it on your calculator?
No, I was probably going to do it.
Okay. That's fine, but understand too that you won't have your computer available to you when it comes to the actual test. So make sure you can do it, by hand as well. But I feel like by writing the code for it, you'll probably have a better understanding of it in that sense too. So, now what I will say, if you can figure out how to program on your calculator, then you might be able to take that in with you into the test. The situation with that is that sometimes they'll make you clear your memory though. So, but sometimes they don't make you clear your memory.
Sean, is that you?
Wait, for number 3,
Number 3 on the homework.
the tangent line, isn't that already the
Don't worry, I
tangent
won't
line?
break anything.
That is the function. To write the equation of a tangent line to a function, you need a point. So you have the x-coordinate, you got to plug in to find the y-coordinate, and you need to find the derivative to get the slope of your tangent line at 0.
It says use the equation of the tangent line
To that. Okay, here is the rest. Here's the rest of your Euler method. There. Okay, you should have gotten approximately 2.1 as your approximation. Okay? Now,
Sean, you're going to like my response. You can't call it though.
You was actually mad about that.
Yeah, but you can still practice. What's the point of going to college when you're just going to get redshirted your freshman year? So you can play it here, Sean. It's the point. I know it's trying to send. I'm not off today.
so way smarter than I am. I'm not smart. That's true. Just convince people that I know what I'm doing. Yeah.
I kind of have a plan. I can see him doing that.
Oh yeah, I'm dormant with like
I have like 15 different plans right now.
What's that? Sorry. Yes. I'll check on that. All right, folks, have a good one. Remember that you are going to block 4. I mean, block 5. You're going to block 5. I know, I'm making it harder.